Okay, so we've got our balanced equation for number one. You should have, at this point, you guys should have all of data table one filled in. I've only got trial one, but you're going to have both, right? You've done C minus D, or I'm sorry, B minus C to get your D, and you've done E minus F to get your G, right? Okay, then for number two, we've started a BCA chart here. Now I'm going to highlight some stuff just to sort of help keep things straight. You do not necessarily have to highlight. I'm just doing it to help us sort of watch what we're doing. So because there's a lot of things they're asking for in this number two. So this is just for trial one. Okay. Which starting material is the limiting reactant? Which material is the excess reactant? So that's one thing they're asking, right? Second thing is they want us to calculate the mass of copper expected. Calculate the mass of copper expected, and we're putting it into data table 2 in slot J. And then the third thing is we need to determine the mass of aluminum expected to react, and we're going to put that data table 2 in spot H. Okay, so there's actually three different things that we're going to be like figuring out with this. Okay. All right. Now, if guys, as I'm going through this, so just keep in mind, I'm using the data from one person. So your data is going to be different, but the steps that you do to solve this are all going to be exactly the same as what I do. Okay, you're just putting different numbers in the spots, but you're still going to run it. So make sure you have your calculators out so you can do the math and all that stuff. All right. First thing, limiting reactant and excess. So the first thing we're going to do is we're going to find the limiting reactant. We need to turn grams of the reactant into moles. So what we started with right here, initial mass of CuCl2 and the initial mass of the aluminum wire. Those are in grams. We're going to turn grams of these into moles. So I'm going to start with the CuCl2. I'm doing mine over here just to kind of fit stuff in here. So 0.501 grams of the CuCl2. We're turning it into moles. So now, here's where the hydrate comes into play. So this, the .2H2O, it's actually part of the compound. So when we're getting the mass for the grams to moles, we have to include that. But luckily for you guys, I'm giving it to you. It's this thing right here. Formula weight, that's the grams per mole. So on the bottom of this conversion, you're going to put 170.49 for the grams down here. 170.49 for the grams of CuCl2. Okay. Now, you guys are all starting with your amount here, correct? Not necessarily what I put unless it's exactly the same. Okay, so divide that. Let's see what we get. Now, if your calculator gives you, there were some calculators that were giving people in scientific notation. So like this, the 2.97 times 10 to the negative third or whatever. Just know that all of our numbers should be really close to the 0.501, like to 0.5 something. So everyone's number should be a decimal point and then 2 zeros. So if it gave it to you in scientific notation, like 2.97 times 10 to the negative third, put a decimal point, 2 zeros, and then your number. You want to take it to three digits, three significant figures. So mine turns out to be 2938, so 294. Okay. So everybody should be 0.2 zeros and then like either two, like in the high two or in the low threes, like 3 something, 2 something like that. If anybody didn't get that, let me know so I can look at it. Okay, that is the moles of the CuCl2 we have before the reaction. So that's going to go here. 0.00294. So you're going to put whatever you got here under your CuCl2. And then we're going to convert the grams of aluminum that you started with, the initial mass from here. So mine's 0.370. You have whatever you have. And we're going to turn grams of aluminum. Aluminum is 27 into moles. Okay. So mine is 0.0137. Again, you want to go to 3 significant figures, 3 non-zero digits, because you don't want to round too much. We're dealing with super small numbers. If you round too much, it's going to really throw your numbers off. Okay. So whatever number you get here is going to go over here in the aluminum in the before. 0.0137. Okay, now, anybody remember what I put in the before for the products? Good, zeros. Okay, so looks like this. Okay. Now, we need to find the limiting reactant. Anybody remember what we do at this step? Okay. Perfect. Divide the moles by the coefficient. In front of CuCl2, there's a 3, so we divide this by 3. In front of the Al, there's a 2, so we divide this by 2. So this I'm squeezing down here for my CuCl. So I do 0.00294 divided by 3. Okay, so now mine is coming up like this. 9.8 times 10 to the negative fourth. So what that means is I put a decimal point, and then whatever my exponent is, I put 1 less 0. So I'm going to put a decimal point, then 3 zeros, which everybody should probably have 3 zeros. So I'm going to do decimal, 0, 0, 0, and then the rest of my number, which on mine is 98. You should go to at least 3 significant figures if you have them. I've only got 2. And then do your next one. And again, if I move too fast or you need me to check something, let me know, please. Okay. So we get those 2 numbers. So even though everybody has different numbers, we should get the same result in terms of the limiting reactant. What's our limiting reactant? Good. This was our smaller number. So our limiting reactant, CuCl2, right? Which means what had to be our excess reactant? Good. Yeah, aluminum, Al. So those 2 things are the answers for our first question, the limiting reactant and the excess reactant. Okay. So we got about a third of that done there. Now, in order to get the amounts that we expect to get, we've got to finish our BCA chart. Anybody remember how to get the change row? Okay. Excellent, yes. You take the smaller number that gave you the limiting reactant, multiply that times the coefficient for each one. So for mine is 0.00098 times 2, which for the first one here gives me 0.00196. Now times 3 is just undoing what we divided by 3 here, so it's just going to be this number. So it'll be the same, so the same as what's above it for the CuCl2. Times 3 is the same as this, so it'll be the same number that you put under the CuCl2. And then times 2 is the same as what you did to the aluminum, so it'll be that number. Okay. All right. Everybody okay with that and have their change row? If you don't, let me know. Like I said, I can come around and help. I don't want anybody getting behind. I'm confused. All right. So let's do our after row. Anybody remember what we do for that? Yeah, Jay.
You subtract the reactant.
Okay, subtract reactants and then add the products. Good. So our reactants, so this, the second one, this one should be 0. This 0.01 for me, or for the numbers I have, I guess, not technically mine. I get 0.01174. 3 significant figures would be 117. Okay, and then these are just the same because they're adding to 0, so. And we have our BCA chart completed. Good. Everybody okay to this point? I don't want, like I said, I don't want to go too fast. Any questions? Okay. Green, calculate the mass of copper you expected to get. So if we look at our BCA chart, where's the amount of copper that the math tells us should be there after the reaction is done? Good. The A row, because that's after, and then under the copper, right? So right here. But we know that everything in our BCA chart is in what label? Good. So mole, so we're going to turn it to grams. So whatever number is in this spot for you, under the copper in the A row, you're going to start with that number, and that is moles of copper, and you are going to convert from moles of copper into grams. Copper is 63.5 for the molar mass. So we get 0.18 minus, well, this is mine, 1866, so 187 grams of copper. So that's the grams of copper that I would expect to get. Okay. So I've got to put that in data table 2 under spot J, under row J. So data table 2, row J, the predicted mass of the recovered copper, you write that number down, whatever number you got, in row J of data table 2. Okay. All right. Yeah. Oh, yeah. Okay, hold on. Yeah, no, but yeah. You're supposed to? Oh, okay, okay. Yeah, much better. Okay. So that gives us the mass of copper. And then did you, so remember data table 2 in row J, where you put that. Okay, now, so that gets us 2 of those. Now we need to do the pink one. And this is the one that can be a little more confusing. Determine the mass of the aluminum that is expected to react during the reaction. Okay, so where in our BCA chart, anybody have any idea where we're going to find that? Okay, good. So the aluminum column, right, because we're talking about aluminum. So the before is the amount of aluminum we have before it happens, right? Yeah, good, Ellie. So actually, we want the C because this is the change that occurs during the reaction. So that's the number. So whatever number you have in this spot, in the aluminum column in the C row, that's the amount of aluminum in moles that was expected to react. So you're going to take that number, and just like we did for the copper, we're going to turn into grams. So this is moles of aluminum is what we have, we're starting with. And we're going to go from moles of aluminum into grams of aluminum, which is 27 for the molar mass. So we just do that. we get, well, you get whatever you get. Mine is 529 grams of aluminum. Okay, so this is the grams of aluminum that we expect to react during the reaction. That answers that part. So we're going to put that in data table 2 in spot H. So that number, data table 2 in row H, the mass of aluminum that should react, you put that number. Okay? All right. How do we feel about what we did for 2? Make sense? Okay, you guys are going to do all of this again for your trial 2, just using the trial 2 numbers. But here's the nice thing. All of the steps are exactly the same. The only thing that's going to change is what your beginning numbers are and then what your numbers are as they work through. But the steps that you do are going to be exactly the same. Does that make sense? So you're going to do your trial 2. You're going to get your beginning 2 numbers here, and then you're going to run through all of these steps, make your BCA chart, do the BCA chart, then turn. You're going to look and see what you have in this spot, turn moles to grams for that. Look what you have in this spot for the second one, turn moles to grams for that, and that's going to be these. And you're going to put those into your data table in trial 2 here. Okay? All right, you don't have to do that now. You're going to do that tomorrow. We're going to go on. We're going to skip number 3. We're going to go to number 4. Okay? Percent yield. Okay? We're going to do percent yield. They give you the equations in the lab here. There's percent yield and percent error. We're doing percent yield for this one. So it's actual over theoretical times 100. Okay, now on our problem, it says use data from G and J. So if we look at G, actual mass of recovered copper, so that's our actual, right? J, predicted mass, the theoretical. So we're going to, so the percent yield is going to be G divided by J times 100. Okay, so let's do it for trial 1. That's how you're going to do both trials, but we'll do the math for trial 1. So take your G, whatever you have in the G for trial 1. Divide it by whatever you have in J for trial 1. Times 100. Okay. Okay, and now if it's over 100, that's okay. Most people's usually are over 100, and we'll talk about that on Thursday a little, but this one happened to not be. But many times people's are over 100. Actually, literally all the other ones I've done, both yesterday and today, have been over 100. Okay, we're going to put this number in data table 2 in spot L. So data table 2, spot L, that's our percent yield for our copper. And put that there. Okay. All right, everybody good on 4? Okay. All right, let's go to 5. 5 is percent error. This is a little different. We've done it before, but it's a long time ago. So percent error, the equation in the lab they give us is the absolute value of the actual minus the theoretical over the theoretical times 100. So it's using actual and theoretical, but a little differently. So if we look, number 5 says use data from D and H. So if we look, D on my data table is, so on everybody's, actual mass of aluminum reactors. That's the actual. The H is the theoretical mass of aluminum. So we're going to do absolute value of D minus H over H times 100. Okay. So for our trial one, absolute value, my D number is, so it's whatever you have here, so minus 0.087 minus your theoretical, which is the H. My H is 0.0529. And then that all over your theoretical times 100. Okay, now, when you do the math of this, remember to do the subtraction first before, and then divide. And if you get a negative number, just make it positive. It's the same number, just positive. Okay, and then go to three significant digits. So percent yield for the data that I have is 64.460.5% for the yield for that. Or percent, yeah, I'm sorry, thank you. That's percent error. Yep. Okay. So that's going to go in our data table 2 in spot I. So spot I is the second one down, percent error for the reacted aluminum. So data I have is 64.5. Okay, so that's going to go here. Everybody good so far? All right. Yeah.
I messed up somewhere.
Okay. No, that's all right. What do you got?
I think it was in the BCA. Yeah. Something over there.
So, oh, that's it? No, that's fine. Oh, you mean your percent? Well, what'd you get for this?
57,000.
Oh, okay. Oh, here's why. You accidentally put 0.001. That should give you a lot closer.
Yeah, this is there.
Yeah, that's okay. And then, except here, be careful. You want this times 100. Oh, that's why you have it like this. It's D minus H divided by H times 1,000. That's why you have the 2 zeros there, so you divide it by it. Yep. Yeah.
I think I don't know.
That's okay. Yeah, for sure. That's not bad at all. Percent error. No. So basically, just so you guys know, the percent error is how close you actually got to what you expected to get. So actually, the lower the percent, the closer you were to the real number. So sometimes and we expect to be off because of some stuff like we'll talk about on Thursday, but we actually do expect to be off. Now, how much you're off? Like I had one data that I was using earlier was like almost it's like 90%. And that's fine. It's not a big deal. It just, it depends. There's different things that could happen. So as long as you're not like thousands of percents, then there's probably some numbers wrong or something, but that should be fine. And then, okay, and then number 6, you're doing the exact same thing except with the numbers for the copper. So it's percent error equals, and it's going to be the actual minus the theoretical, so if we look up in number 4, your actual is G, because it's G and J still. Your actual was G and your theoretical was J. So it's going to be absolute value of G minus J all over J, and then times the whole thing times 100 to get a percent. Okay, so for trial 1, and again, you don't even have to go to your data table for this because you've got all the numbers in number 4. So percent error equals, my actual is the one on the top here, so it's 0.176 for me, minus my theoretical is the one on the bottom, 0.178, or 187, I mean, all over my theoretical, 0.187, then times 100. So we do that, and we get if you get a negative, you just make it a positive. So for my data, hey, this one's super close. It's 5.88%. Okay. And then we're going to put this number in the last spot in our trial on data table 2 in spot K. So that's going to go trial 1 in spot K, should be the last open spot you have in trial 1, 5.88%. Okay. All right. So I'm going to stop this.